polynomial functions. You guys are going to learn how to graph polynomial functions. Now, I'm not just talking about quadratic functions or linear functions. I'm talking about all types of functions, cubics, quartics, and so on and so forth. Okay? So, let's talk about some terminology. Here we go. A polynomial function of degree n of a function is in this form, which you see in the black. Okay? A sub n represents what's called the leading coefficient of the polynomial. Okay? And n is called your degree or your exponent, either one. Okay? So a sub n, x to the n basically represents one of the terms. So that's something like 3x to the 5th power. Okay? Plus a sub n minus 1 times x to the n minus 1 plus so on and so forth until you get down to where there's just a constant. Okay? So n is a non-negative integer, a sub 0, a sub 1, so on and so forth are all real numbers, and a sub n cannot equal 0. Okay? So an example like that, like I said, could be 3x to the 5th power minus 4x to the 4th power plus 7x to the 3rd minus 8x squared plus 16x minus 2. That's an example of a polynomial function. As you can see, your exponents are decreasing. That's in standard form. Okay? And then your leading coefficient in this case would be what number? 3. Okay? You always want to identify where the largest exponent is. Okay? What term the largest exponent is, because sometimes it won't be in the front. If it's not in standard form, it could be somewhere else inside of that polynomial expression. But once you find it, then that will help you determine your end behavior, which you guys practice today for your do now. Okay? So again, the leading coefficient of a polynomial is the coefficient of the variable with the greatest exponent. And that leading term that has the largest exponent, also known as degree, you use that term, like I said, to determine its end behavior. Okay? So you always want to identify where it is in the expression, and then go from there. Review. This was on the exact same tan-colored, ivory-colored paper when we were talking about polynomial functions. When n is odd and a sub n is positive, in other words, your degree, your exponent is odd, and your leading coefficient is positive, it's going to be a graph that looks like this, where the right side goes up, the left side goes down, and there's something happening in the middle. And we're going to talk about what happens in the middle later. When n is odd and a sub n is negative, it goes the opposite way. The left side's up and the right side's down. When n is even and a sub n is positive, both sides go up. And when n is even and a sub n is negative, both sides go down. We've talked about this. You did an activity with it today. You were introduced to it in power functions. Hasn't changed. Now that we're talking about polynomial functions. Okay? So, let's describe the end behavior of each of the polynomial functions using limits. Okay? And we're going to justify our answer. So basically, we're going to figure out which one of the 4 graphs it is. Okay? What is the largest degree in A? 4. So you identify where it is, and that's the term that you're looking at to determine, okay, what type of end behavior am I looking at? Is n even or odd? Even. And is a sub n positive or negative? Positive. Positive, which means that this graph is going to be up on both ends. Which means when we describe that end behavior using limit notation, so the limit as x approaches infinity of f of x, is that the right side or the left side of this function? Right. The right. So if I'm looking at the right side, which is right here, is that positive infinity or negative infinity? Positive infinity. Good stuff. And then the limit as x approaches negative infinity, which will be the left side now. So not this side. Is that positive infinity or negative infinity? Positive infinity. These polynomial functions are not going to have any type of discontinuity. Okay, they're going to be continuous functions, so it's either going to be positive infinity or negative infinity when you're looking at their end behavior. Okay, no specific value. What about B? What is it? Same question from before. What's the largest degree? 7. The 7. So that means, as you can see, it's not the first term, but it is the one with the large exponent. That's the one you want to use. Is n even or odd? Odd. And is a sub n positive or negative? Negative. So because that happens, and you look right above on your notes, you can see it's the one that's up on the left, something happening in the middle, and down on the right. Correct? Okay. Go ahead and do that in behavior real quick. What is my right in behavior as x is approaching positive infinity? Negative infinity. And as x approaches negative infinity? Positive infinity. Very good. What about 3? What is my largest exponent? 3. So that means I'm using this term right here. That coefficient, is it positive or negative? It's positive. It's a positive 1. And it's odd, which means that it's going to be up on the right and down on the left. So the limit as x approaches infinity of f of x is positive infinity, and the limit as x approaches negative infinity is negative infinity. You guys kind of already did this. Okay? Now we're just putting some terms to it. Any questions? So that's the ends of these polynomial functions. Let's look on the inside of these functions. Okay? Maximum and minimum, which we talked about as extrema back in Unit 1, are located at turning points. Okay? A polynomial function's degree of n has at most n distinct real zeros and at most n minus 1 turning points. So let's talk about this. Maximum and minimum. Those are humps in the graph. Humps or valleys. Okay, these are maximas, these are minimas. Okay? When we talk about distinct real zeros, what's another word for a zero? It's an x-intercept. Okay? And when we talk about turning points, we're talking about where it goes from increasing to decreasing, decreasing to increasing. So you'll always know at least how many x-intercepts you should have and how many turning points you should have based off of the degree of the polynomial. Okay? So for example, we're going to state the number of possible real zeros and turning points of the function x to the third minus 5x squared plus 6x. And then we're going to determine exactly what those real zeros are. So, first thing we need to know is the degree of this polynomial. What's the degree of this polynomial? It's 3. So because n is equal to 3, that means that we'll have at most how many real zeros? How many? We'll have possible zeros is 3. So we'll have at most n distinct real zeros, so we'll have at most 3 zeros, and then how many turning points? You'll have 2, okay? Because you'll have at most n minus 1 turning points. So at most n real zeros and at most n minus 1 turning points. Okay? So basically the graph again will go from increasing to decreasing or decreasing to increasing. And to determine these real zeros, you set the equation equal to 0. And you solve. What do you see in every single one of these terms? An x. So if I factor that out, and I want to factor out, not divide. When I factor out an x, that leaves me with x squared minus 5x plus 6 equals 0. Can I keep factoring the inside? What are the two numbers that multiply to give me 6 that add together to give me a negative 5? So one's positive, one's negative, but which one's the positive, which one's the negative? 6 or the 1? 6 is negative and 1 is positive. Because remember, we're looking for the two numbers that multiply to give us 6, add together to give us negative 5, and the only way that can happen is if the 6 is... Yeah. Oh, no, that doesn't work. It's going to have to be negative 3 and negative 2. Because this won't give us a positive 6 if we multiply it. So we got to do the other two numbers, which are 3 and 2, and both of them have to be, oh my goodness. Both of them have to be what? Negative. Now I say each one of my factors equal to 0. So that's x equals 0. Yes, we need to make sure we set the outside factor equal to 0. X minus 3 equal to 0, which is just x equals 3. And x minus 2 equal to 0, which is just x equals 2. And here we go. These represent my zeros, my x-intercepts. And that's what I could possibly have at most 3 of them. And I have 3. Questions? Well, like for this question, yes, for this question, not like for this. All right. We're going to do another one together. Okay? Let's state the possible number of real zeros and its turning points, okay? What's the degree? So that means I have how many possible zeros? How many turning points? Say it with confidence.
3.
It's 3 because it's always one less. Always one less. Now we have to determine what our real zeros are. Each one of these are different. Each one of the examples we're going to do are different. But they all are solved, or we can find the zeros by using factors. You just have to recognize what type of factoring you got to use. For the last example, you had a GCF, and it was just a regular find two numbers. This one, you're still looking for two numbers, but you notice how your degree is larger. It's not like x squared and then x, right? It's double, which means that when you factor it, this won't be x and x. It would be x squared and x squared. Because x squared times x squared is x to the 4th, right? Okay? So what two numbers multiply to give you negative 4 that add together to give you a negative 3? Negative 4 and positive 1. But now I have a further question for you. Can I factor any of those further? Or do you just want to set both of them equal to 0 and keep going from here? You can, but I worry. If I set both of these equal to 0, and I solve this one over here on the left, what do? Add 4. Square root both sides, and x equals? And that's what I was worried about. Half of y'all said 2, and the other half said plus or minus 2. Which one's the correct answer? It's plus or minus 2. Because whenever you're taking the square root in an equation, it's always positive and negative that number. Well, possibly 4. That's 2 of them right there, a positive 2 and a negative 2. But when I do this one over here on the right, I'm going to need to subtract 1, and then when I take the square root, you can't take a square root because it's a negative number. So there's none here. If this had been a positive one, yes, there would have been our 4 zeros. But it says at most 4 zeros is what we can have. In this case, we only have 2. And that's okay. So our 2 zeros are x equals 2. and x equals negative 2. Questions? Because that's the possible number that you could have. You could have up to 4 zeros, but you could have less. And real quick, x squared minus 4 can factor to be x minus 2 and x plus 2. That's how you end up getting one positive 2 and one negative 2. Remember, difference of perfect squares, SATs next weekend. Okay? Don't forget about those. Last one on this page. And it's another one that's a little bit different, but we're still going to use factoring to find the number of real zeros. But first, how many possible real zeros can I have? How many turning points? So now to find what they are, I need to set the function equal to 0. And I'm going to have to do the factoring method that is rarely taught, or it's just delayed scope. Anybody know that method? Andy, you kind of use that method when you factor, or you used to. I don't know if you changed over. To factor this, you factor by grouping, and how you factor by grouping is you group the first two terms of the polynomial, and then you group the last two terms. And what you do is you determine what's the GCF in both of those groups. So when you look at the first group of 4n to the third minus 7m squared, what is the GCF? M squared. And then that leaves you with what from the first group? When you do the second group, the goal is to make sure that the inside is the exact same as what you got for the first group. What's the GCF for the second parenthesis? Positive or negative? It's positive. And you'll always know what the sign is. Now, I'm putting a plus 8 for a reason. You always know what the sign is because of whatever the sign is of the third term, that's always going to be the sign of, like, inside of the, for the GCF. What's that word? When I take out an 8, what am I left with? 4m minus 7. They're the same. That's what you wanted. The two factors of how what's in the orange factors down is what's on the inside, which is 4m minus 7, and what's on the outside, m squared plus 8. That is how the orange factors. You only write that 4m minus 7 once, because it's like you're taking the GCF from both terms. That's how you factor by grouping. That's how you do a 4-term polynomial when you're factoring. Set both of them equal to 0. And solve. M equals 7 over 4. And when I solve this one, what happens? When you take the square root, you can't do it. So there's only one actual real 0 for this one. And it's 7 over 4. Your other two are what you call imaginary, which can happen. So that's how you determine what's in the middle. So we talked about what happens on the ends. We talked about what's happening in the middle when it crosses over the x-axis, okay? Or actually crosses or touches. This is that last little bit on your on this page. The factor x minus c occurs more than once, then it is a repeated 0, and that's known as multiplicity. So let's say that when you factor that one of your factors end up being x minus 2 squared. Okay? That's technically x minus 2 times x minus 2. It occurs more than once. The multiplicity is the repetition of the 0. So when a 0 has an even multiplicity, like this one does, the one that I just wrote up there, the graph will be tangent to the x-axis at x equals c, and the value of the sign does not change. So, what does that mean? Does anybody know what tangent means? It means to be, it means it doesn't cross, it actually means it touches. So tangent means that it touches the x-axis. Okay? So if you have an even multiplicity, that means that the curve of the function that you're graphing is going to touch the x-axis at that x value, and then the sign does not change. So it's basically going to ricochet off the x-axis. So let's say it's coming down, it's going to ricochet off at that x value. That's what that means. So it can do it either in the positive direction or in the negative direction. It's pretty much based off of what the ends are for that function. But when a 0 has an odd multiplicity, then the graph will cross the x-axis at that point, and the value of f of x will change. So when it's odd, such as, like, let's say you have x minus 1 and x plus 3. Both of these have an odd multiplicity because their exponent is both 1. So that means the graph is going to cross the x-axis at x equals 1 and x equals negative 3. So it's going to cross, and then it's going to cross again. Okay, that's what that means. So now we have all the information that we need to graph a polynomial function. We know about its end behavior, we know how to find the zeros, and we're going to know when the graph is either going to cross or touch the x-axis. So let's put everything all together. For f of x equals x times 2x plus 3 times x minus 1 squared. That's a polynomial function. That's already what? It's already factored. Okay? So, if you look at the degree of each one of these factors, you have an x, that's a factor, that's a degree of 1. 2x plus 3 has a degree of 1. The air cut on, so I definitely couldn't hear you. And then x minus 1 has a degree of 2. 1 plus 1 plus 2 is 4. This is a polynomial that's to the 4th power. I don't actually need to multiply it out to try to determine what the degree is. I know, based off of the multiplicities, what power it is. All we do is add them. And is a sub n positive or negative? And you know it's positive because look at the coefficients. This is positive, and this is positive. Positive times a positive is a positive. So again, look at the degrees, look at the multiplicities to determine the power, and then look at the coefficients of each one of those factors to determine if it's positive or negative. So if it's an even power and a positive coefficient, the right end behavior is going to go up or down? Up. And the left end behavior is going to go up. Because it's even, it's positive, which means it looks like this. That was the first thing that we did today. Now let's determine the zeros and state the multiplicity. Well, this one's kind of nice because it's already factored for us, right? So all I have to do is set each of the factors equal to 0. X equals 0, it's already solved. What's its multiplicity? Remember, you look at the degree, the exponent, to know if it's going to be what it is. So what's the exponent? It's 1, which means it's odd, which means it's going to what on the graph? Cross it. When I solve this, x equals -3/2. What's the multiplicity for this factor? So at -3/2, the graph is going to cross again. And when I solve the other one out, x equals 1. What's the multiplicity here? Which means the graph is going to touch. Now let's graph this. You really don't have to find any few additional points. Really what I'm going to be looking for when it comes to these graphs of polynomial functions is your end behavior right. Are you crossing or touching at the x-intercepts where you're supposed to be? And are you at the correct x-intercepts? I could care less about where it crosses the y-axis or, if it goes as high as it's supposed to go. Okay, I'm not concerned. But if you forget everything else, you can always go back to making a table to get the graph of the function. You can always go back to that. Okay? No matter what. Hence the finding additional points. So I know my end should be up here. Okay? So if I'm coming from my left end behavior, I should, the first x-intercept I'm going to come across is x equals -3/2. And I'm going to do what at that point? I'm going to cross. So I'm coming down. I'm going to cross at -3/2. I got to turn at some point because I got to come back up and what's my next x-intercept? 0, and I should cross, and then I'm going to have to turn again because I have to make another x-intercept where? At 1, but which means I'm going to ricochet off of that bad boy. So I'm going to ricochet off at 1 and continue to go up. And that's how you graph your polynomial function. Okay? And then, of course, go back in and make it pretty because that's just ugly. There we go. I'm going to erase this extra one because that's just terrible. All right. There you go. You okay? Yeah. It's a lot. It is a lot, okay? But the main thing is determine your end behavior so you know what's happening at the ends. Find your zeros. Determine if it crosses or touches. And then go from left to right based off of whether you cross or touch that x-intercept. And everything's always hard when you do it the first time. That's why you got to do it, multiple times to get good at it. Let's take a look at this one. Let's talk about our end behavior. Is n positive? Is n even or odd? Odd, because it's to the third power. And is a sub n positive or negative? Negative, which means based off of the notes earlier, this graph should look like this. Which means when I describe the end behavior, because I have the exact same directions as we did from the other one, if I look at the right side of the graph, it's negative infinity. And if I look at the left side of the graph, it is now this one isn't factored like the other one was. But I can factor it. What do you see in every single term? At x. And trust me, to make your life easier, since it's a negative leading coefficient, why don't you factor out a negative x? Because when you factor out a negative x, what's the first term going to be? A positive x squared, then it's going to be a negative 2x, because I'm taking out not just an x, but also a negative. So that means that this had to be a negative 2x in order for it to become a positive 2x squared if I were to distribute it back through. And then when I take a negative x out of an 8x, what? It's a lot easier to factor. What two numbers multiply to give me negative 8 that add together to give me negative 2? Well, one of them has to be, the 4 is negative. Now, real quick, all of my multiplicities are what? They're all odd, which means that every single one of these zeros is going to cross, because all the multiplicities are 1 for all 3 of these zeros. You can always determine the multiplicity from the factor form before you actually go on and solve, okay? It's the exponent of each one of the factors. So now when I set each one equal to 0, I can solve and find my zeros. X equals
1,
0. Divide by negative 1. X equals
4,
4, because I would add 4 to both sides. And x equals, because I would subtract 2 from both sides, and every single one of those have a multiplicity of 1. So I'm at negative 2, 0, and 4. And in every single one of those, I'm going to cross. My ends, the left side is up, while the right side is down. So I'm coming from positive infinity, coming down, crossing, crossing, crossing. There's your function. And remember, I am not concerned about how high it goes or where the y-intercept is, even though I know this one says 0 because it's 0. More concerned about do you cross at the correct x-intercepts? Do you have the correct end behavior?
How do you start? Like, how do you know where to start?
You always go from left to right. So wherever the end behavior is on the left-hand side, if it's up, start in the up position and go down. Or if it's down, you start from the down position and go up. Yes?
What did you mean by, like, ricocheting for the first example?
Because, so for the first example, because the multiplicity was a 2 for x is equal to 1, that means it's going to touch, which means that when it touches the graph, it's not going to touch and cross through the x-axis, it's going to bounce off the x-axis. So when I say ricochet, I'm basically like bouncing off of that x-axis, like I'm hitting the ground and bouncing back up. Do not cross over at that point. Okay? It's bouncing, it's touching. Any questions? Yes?
What is this multiplicity? It means kind of like the exponent that it has, the factor part.
Of the factor, yes. So multiplicity is like the exponent of the factors. Okay? Any others?
And you said it doesn't matter how, like, tall.
Doesn't matter how tall. The only way you're going to know exactly how tall it is if you were to plug in like 1 or 2 or 3 into the function to see exactly how high it goes. And this one actually does go pretty high, but I'm not concerned about that. And that is how you graph a polynomial function. You use the end behavior and the zeros to determine what the graph looks like.